Okay, so in the last lecture, we were looking at the MOSFET as a barrier control device or a voltage control device. So of course, you looked at how you can apply a gate voltage to attract electrons just below the gate. And that's how you actually form the channel. The channel does not exist in the beginning, but as you apply a positive gate voltage, you attract more and more number of electrons just below the gate, which means that the region just below the gate becomes more and more inundated with a large number of electrons. Now, of course, the source and drain already has a large number of electrons. If you have a region in between which also has a large number of electrons, you can assume that as a continuous region of N-type silicon, right? And that's how we form the channel, and that's how the conduction occurs from source to drain in terms of the majority carriers. You also looked at the energy band diagram representation of how we can explain it from the point of view of physics or device physics. And as you know that if you apply a positive voltage, the energy of an electron reduces, right? And if you have more number of electrons, which happens at the source region. So for example, if I mark this as the N-type source, then you have an N-type drain, and in between, let's say you had a P-type channel, right? So that's how the MOSFET looks like. So if I draw the MOSFET structure, this is how the N-type source looks like. This is how the N-type drain looks like. And you have a gate in between with an oxide layer acting as an insulator. So this is basically your metal. Then you have an oxide layer here, and below it you have everything is semiconductors, right? Now, if you apply a positive potential at the gate, you know what will happen is that the energy of the electron will reduce. The overall energy will reduce. That means this barrier, this energy barrier that you had initially, that will come down. So initially you had something like this, which was, let's say, a high boundary wall, and then that boundary wall just comes down and becomes a low barrier, right? So if you have an electron on this side, it becomes easier for the electron. What is easier for the electron? To jump up and cross that barrier like this, or just roll through and cross this barrier like this? The second scenario is much more easier for the electron, right? And that's what happens when you apply a positive gate voltage for the MOSFET. All right. Now, as you apply a positive gate voltage, you know that you're reducing the barrier. You're reducing the barrier height. But if the left side is at, let's say, the same voltage as the right side, so let's say you have VDS equal to 0. So if I go back one slide, you'll have VDS equal to 0. And in that case, you had this flat barrier. On the other hand, if you apply a VDS, drain to source voltage greater than 0, remember again, this side is source, this is basically the channel in between, and this side you have drain. So if you apply a VDS which is greater than 0, that means again you're applying a positive voltage not only to the gate, but you're also applying a positive voltage to the drain side. So you apply a positive voltage on the gate, you also apply a positive voltage on the drain. If you do that, of course, you know that there will be a current flow from drain to source because drain is at a positive voltage, source is at a lower voltage, current flows from higher voltage to lower voltage, as simple as that. But again, from the energy band diagram perspective, if you apply a positive voltage at the drain, the barrier or the energy or the conduction band energy on the drain side, that goes down a bit. So earlier you had this dotted line. Now you have this solid blue line or solid dark blue line, which is going down on the drain side, right? Now, what does that mean? That means that if you have an electron and if you have a little bit of energy to push that electron, if you have an electron on the source side, and if you have a little bit of energy to push that electron over here, then that ball or the electron just rolls through this barrier, goes to the drain side. It becomes even more easier for the electron to go from the source to the drain if you apply a positive drain voltage. Just imagine that this is a ball rolling through a hill. First, you have reduced the height of that hill, and then you have made it a slope so that the ball just rolls through without applying much energy. That's exactly what happens inside the semiconductor device. Now, if you keep on applying more and more drain voltage, so what you see here is what will happen if you keep on applying more and more drain voltage. So first you had this with zero drain voltage, then you applied a little bit of drain voltage, then you keep on applying more and more drain voltage, and you start seeing this. So what does that mean? That means the slope is higher and higher as you apply a drain to source voltage which is greater than zero, and you're applying higher and higher amount of drain to source voltage. So more and more number of balls or more and more number of electrons are going to roll through that slope, and it will roll through very fast. And if electrons are rolling through fast, that's basically higher amount of current. And again, it makes sense because you're applying more and more voltage, you're getting more and more current. That's it. Yes.
So as we apply more and more drain source voltage, the slope clearly gets steeper, but there's still a bump at the very start.
Yes.
Does that bump change as we apply more voltage? And can you think that bump is like the forward voltage of time?
Yes, exactly. That's a very good point, that there is still a bump over here, right? What does that bump signify? That without applying, so remember that here what you had is originally this much amount of height of the barrier. You applied a gate voltage, and even after applying a gate voltage, there remains a little bit of bump. So you still need to have a little bit of energy in those electrons to make sure that they like roll up the bump, and then rolling down is not a problem at all. So what that signifies is that you still need a particular amount of threshold voltage for the electrons to pass from source to drain. So any MOSFET will have a threshold voltage, just like the diodes had a threshold voltage. And that threshold voltage is basically when the amount of gate voltage that you need to apply before your MOSFET even starts conducting, before you even start forming a channel. All right. So that's what is happening. Now, one thing that is interesting, if I can go back, is that as you keep on increasing the drain to source voltage more and more, you'll see that the slope will become more and more, higher and higher. But after some point, let's say the slope has become exactly like this. So you cannot increase, even if you increase the VDS more, you cannot increase the slope anymore. So after a certain point, even if you keep on increasing VDS more and more, you'll not get more number of electrons passing from left side to the right side. Right? Because at some point it just becomes a slope of 90 degrees, and then you cannot do anything after that. Which means that after a certain VDS, after a certain positive VDS, even if you increase the VDS, the amount of current or the number of electrons that are moving from left side to right side in unit amount of time, that will not change. And that is actually denoted as the region of saturation, that the current saturates and current does not increase anymore. Remember that we drew this particular curve, that if you put your VDS on the x-axis and you put your ID current, the current flowing between drain and source, on the y-axis, as you increase your VDS, you'll see a linear increase in the current at first. So that is basically this slope increasing more and more. And because the slope increases, or the absolute value of the slope increases, you get more and more current. But after a certain point, it saturates and you see a saturated curve like this. That means that after you have increased VDS by a certain amount, you cannot have more number of electrons flowing from left to right because it is all saturated and the slope cannot increase anymore. Okay, now let's say you remove the gate voltage. If you remove the gate voltage, the problem would be that your VG is 0 or VGS is equal to 0. You still have a high barrier. So the electron over here, that still has to go up, cross this barrier and go to this side. So that cannot happen. So this is the region where you have cut off, or you have cut off the amount of current flow. Even though your drain is at a positive voltage, your source is at 0. So you have a large drain to source voltage. So you have a large amount of slope over here, but that slope does not matter because the height of the barrier is too big. So if the height of the barrier is too big, which happens because you have not applied a gate voltage. So if you have removed the gate voltage, the height of the barrier goes back up and you cannot have any kind of current flow, and that is the region which is called cutoff. Question? Exactly, that's a great point. So what we are learning here about MOSFETs is that they operate in different modes. They can operate in cutoff versus on, so that is off versus on, which is what digital, if you take a digital circuit course, That's all you learn, that MOSFETs turn on and turn off. It's a switch, right? The MOSFETs do work as a switch, which is when the MOSFET is off, you're in the cutoff region. That is, you're applying a VGS for that, let's say NMOS, your VGS is equal to 0. On the other hand, if you apply a positive VGS for your NMOS, then you're on, right? So that is on and off. Now, when you are on, you can still have different amount of currents passing through it, depending on how much VDS you have applied and what is the slope of this particular barrier on the right-hand side, right? And then it saturates at some point. And that's where analog circuit designers are interested in. Analog circuit design is not on and off. On and off is digital, because digital is binary, as you know. And what binary means? 0 or 1. 0 means off, 1 means on. However, there are things which are between zeros and ones. That's where analog circuit designers are interested in. That's what mostly we'll learn in this next few lectures. And then we'll also look at digital circuits using MOSFET. So we'll learn both in this course. All right. So if your gate to source voltage is lower than the threshold voltage required, then you are in the cutoff region. This is what ID versus VDS characteristic looks like for a real MOSFET. So till now, we are just drawing cartoon hand-drawn diagrams. This is from a real MOSFET, which you can, so for example, just like you had your 1418 diode, you can have a MOSFET you can buy from the market, and then you can figure out how the characteristic looks like with respect to VDS. And all these different curves are for different VGS, gate to source value. So your VGS, gate to source, is actually increasing as you go up. So the lowermost curve is for a very low VGS. The uppermost curve is for the highest VGS that you have. Now, interestingly, what you see here is that the curve kind of saturates. It does not actually saturate. Right? So that's a non-ideality of a MOSFET. Ideally, you should have seen all these curves saturating like this. Right? But as you see that even in the saturation region, they have a slope. I mean, if they were ideal, the slope would have been 0. If they had been ideal, the curves would have been parallel to the x-axis, and parallel to the x-axis means slope is equal to 0. But real MOSFETs do not have slope equal to 0, even in the saturation region. We'll discuss those non-idealities, but it is kind of saturating, right? It's not changing as much as it was changing in this region. All right. So now if you want to mathematically show that what is going to be the IV characteristics and what is going to be the equation. So at the end of the day, we are circuit designers, and we'll try to solve numerical problems related to MOSFET. Till now, what you have learned is qualitative. Hopefully you have built some sort of an intuitive understanding of how the MOSFET behaves. But now we are actually going to look at equations, we're going to prove equations, and we're going to use those equations in numerical problems. All right. So now if you want to mathematically treat the MOSFET, okay, and let's say you want to do it for a small VDS, because you know that there are two regions. If you plot ID versus VDS, assuming that, of course, the MOSFET is on, so it's not in the cutoff region, which means that the VGS, the gate to source voltage, is higher than the threshold voltage. Assuming that, your ID versus VDS looks like this, right? So there is a region where it behaves linearly, the current behaves linearly with the voltage, and then there is a region where current saturates and is not a function of the voltage anymore. So first, let us look at a region where you have a small VDS. That is, you are looking at VDS values less than a particular amount in this particular curve. Now, again, from your high school physics, you know Q, that is charge, is equal to capacitance times voltage. Why we are looking at this equation? That's because as you are looking at this MOSFET structure, let's say you have a gate to source voltage greater than the threshold. And if you have that gate to source voltage greater than the threshold, you'll form a channel, right? So if you did not have the gate to source voltage greater than the threshold, you do not form the channel over here. The channel is formed only if the gate to source voltage is greater than a particular amount of threshold. And that's because as this voltage is positive, you start drawing electrons from the bulk region. You also draw a few electrons from the source and drain regions. So you get excess of electrons just below the source. And excess of electrons is basically saying that you have effectively an n-type region, because n-type regions have excess of electrons. P-type regions have excess of holes. Okay. So to form a channel, you need to apply a positive gate voltage if this is an NMOS. So we'll treat everything as an NMOS for the next few lectures. Later, I'll show that PMOS also behaves in a very similar way. It's just the dual of NMOSes. So let's just think about NMOSes for now. So you have to apply a gate voltage which is greater than 0 and greater than a threshold voltage to form the channel. Now, if you think about it, the gate is a metal, you have an oxide, and then you have a semiconductor. So you have a MOS structure or a metal oxide semiconductor structure, which is nothing but a capacitor. A MOS is a capacitor because metal is conductive, oxide is insulator, and semiconductor, when it is doped, when it has excess of electrons, it is a conductor. Right? So doped semiconductor is closer to a conductor, and undoped semiconductor is a semiconductor because it has a conductivity which is in between metal and insulators. So you have a capacitor, and the charge that is stored in that capacitor is C times V. If the capacitance is C and the voltage across it is equal to V. Now you can write the capacitance as epsilon A over T, or basically the distance between the two plates of the capacitor is in the denominator. And that is called the thickness of the oxide layer. So this oxide layer has a particular amount of thickness that is equal to your Tox. The thickness of the oxide layer is thickness subscript oxide. And you know that capacitance, the formula of capacitance is epsilon A over D. Epsilon is your permittivity of the material. A is the area of the capacitance, capacitor plates, and Tox is basically the distance between the two plates, in this case, the thickness of the oxide layer. All right. Now, if you want to represent the capacitance per unit area in circuit design or in terms of MOSFETs, that capacitance per unit area, that channel capacitance per unit area is termed as COX. And this is universally true, right? So any book that you study, if you come across this term COX, that will mean the capacitance per unit area for the capacitor that is formed between the metal gate, the oxide, and the channel. So COX is basically C divided by A, that is just epsilon OX by TOX. So oxide's permittivity divided by oxide's thickness. So that's the capacitance per unit area, and the unit for that would be, let's say, farad per centimeter square. All right. Now, what would be the charge in the channel in that case? The channel charge would be equal to minus of COX times VGS minus VT. And this is the channel charge per unit area once again. And what do we mean by area? Of course, you have a length. So let me change the color. So of course, you have a length. And then remember that the MOSFET is a three-dimensional structure, right? So it also has a width. So if I draw the 3D figure, it will look something like this, right? So I'm not drawing it correctly, but then of course, you have a width which is in the other direction, the other dimension, which is not shown in this particular figure, right? So this length multiplied with the width, that is basically the area of the channel. And remember that we had shown a top view of the MOSFET. So the length and width were both there in the top view of the MOSFET. Length multiplied with width, that's your area. All right. So if you now have the capacitance and the voltage multiplied with capacitance and voltage, that gives you the charge. Now this charge is the charge per unit area. Why? Because you have taken the capacitance as the capacitance per unit area multiplied with the voltage in the channel. Now, of course, you are applying VGS, right? But nothing happens unless that VGS is more than a threshold voltage, right? The channel does not form unless the VGS is more than a threshold voltage. So when the channel is formed, the voltage that you have in the semiconductor is basically VGS minus VT, because you can think of it as the drop that happens from the metal to the semiconductor. So there is some amount of drop in the voltage that happens from the metal to the semiconductor, and that drop is basically will be equal to your threshold voltage. That if you apply let's say a positive voltage of 0.5 volt, you may not see the channel being formed because the voltage that you actually see in the semiconductor will be less than zero, even if you're applying a positive voltage. Only if your voltage is higher than the threshold voltage, you see something happening in the semiconductor region. So what matters for the semiconductor region is how much higher you are as compared to the threshold. If you're below threshold, equal to threshold, does not matter for the semiconductor because the channel is not formed. Only if you are above the threshold, your applied voltage at the gate is above the threshold, it matters for the semiconductor region because then only the channel gets formed. So the voltage that effectively the semiconductor region will see is VGS minus VT. So that's the voltage. What is the capacitance? Cox, that's the capacitance per unit area. So the charge per unit area is going to be the capacitance multiplied with voltage. That's all I have done here. Now, why is this negative? Why is this minus? That is because your charge is created by electrons, right? And electrons have negative charge, and that's why I'm putting a negative sign for the charge over here. So again, remember, this is the charge per unit area. And how is area defined? Area is defined as length multiplied with width. So length is this, the distance between your source and drain regions, and width is basically the dimension perpendicular to the plane of the screen over here. So this dimension is not drawn, but the dimension, the third dimension over here is going to be the width. All right. Now, the VGS minus VT, this term we'll be using a lot over the next maybe 10, 15 lectures. So instead of calling it VGS minus VT, VGS minus V threshold, and what does N signify? N signifies that this is an MMOS. So that's why you have VTN. If it were a PMOS, we'll call it a VTP, the threshold voltage for the PMOS transistor. So VGS minus VTN will be called the overdrive voltage, VOV. So we'll be using V overdrive a lot in the next 10, 15, 20 lectures, like maybe till the end of the course even. And this is called overdrive because this is the voltage that is in addition to the threshold voltage, whatever you're using to drive the transistor. So it is an overdrive voltage that in addition or above your threshold voltage, this much amount of voltage you are applying. So V overdrive is just VGS minus VT. So if your V overdrive is positive, that means you're above the threshold voltage and you have formed a channel. If overdrive is negative, nothing happens. And VTN, as we said, that it's the threshold voltage. Now what we want to do is write down a few equations. So first of all, what is the current through the device? What is the current through the device? If the charge per unit area is Qn of X, that's what we defined in the last slide. The charge per unit area is Q. Now, of course, what is the charge per unit area? That's, let's say you draw this third dimension over here, something like this, and then you draw the other dimension. Now, what you basically have in the channel, so if I draw this part, which is the channel in 3 dimensions. So you might see something like this. So this is what we are seeing, just a 2-dimensional rectangle. That's what we are seeing right now. But in reality, this is a 3-dimensional structure. Okay, this is the width of the channel, and this is the length of the channel. The charge per unit area is basically the charge per unit W times L, because area is W times L. So the charge is the charge that is present in a small, let's say, section like this. So if we take a cross section, of that this rectangular bar or parallel pipette bar, the charge that is present in this cross section is Qn of X, right? Because charge per unit area is what? You have to make area equal to, or basically the unit amount of W and L. So for that, you will have Qn times W. So the total amount of charge that is present in this cross section, So remember, for this cross section, the length is very close to 0 because it's just a cross section. It's just a section on this bar, but the width is equal to W, right? The width is still equal to W. The amount of charge present in unit area was Qn. So the amount of charge that would be present in this cross section would be W times Qn. W times Qn is the amount of charge that is present in this cross section. Now, what is current? Current is this charge flowing through the channel. So this cross section, if this cross section keeps on moving through the channel, that's when you'll have current. And the velocity of that, so basically let's say Vx, that determines the velocity of the charge flowing through the channel. That is the velocity with which this cross-sectional charge moves through the channel. Right? That's basically your current. Current is equal to total amount of charge divided by the time. So the total amount of charge is W times Qn moving through this channel at a certain velocity. And if you multiply that with this cross-sectional amount of charge, you'll get the total amount of current. Now, Q is equal to minus Cox times Vgs minus Vt from the previous slide. And the velocity of an electron in the channel is generally given by, again, this goes back to your device physics classes, so I'll not discuss this in too much detail over here. The velocity is given by mu times the electric field in the channel. So mu is called mobility. You may have heard about this term, mobility of electrons, mobility of holes, and so on. So mu is mobility and E is electric field. Mobility times electric field gives you the velocity, or basically mobility is the proportionality constant that relates the velocity with the electric field. If you have subjected your electron to your electric field, the electron will move at a certain velocity, and velocity will be mobility of the electron, that's the proportionality constant, multiplies with electric field. So Vx is going to be minus mu times E, or electric field. So you just put those two values over here. Also, you can note that the electric field effectively is dV dx. So if you want to do an exact calculation, electric field is minus dV dx, derivative of the voltage with respect to the length. But if you approximate, it's the voltage difference between source and the drain divided by the distance between the source and the drain, right? So dV dx is the exact value, minus of dV dx, but you can approximate it as minus of VDS over L, because the dx, the distance between the source and drain, is L. The dV, that is the voltage difference between source and drain, is VDS. Now, of course, this will lead to an approximation. I'll also show how to do the exact calculation. That's another document that I have uploaded in Canvas. But if you put all of these things in the first equation, in this equation, if you put the value of Q, if you put the value of Vx, and if you put the value of E, what you're going to get is this equation, ID equal to W over L times mu and Cox times Vgs minus Vt times Vds. How? Of course, you had your W. Instead of Q, you put Cox times Vgs minus Vt. So you have Cox times Vgs minus Vt. You already have your W. Vx represented as minus mu times Ex, and Ex is represented as minus Vds over L. So you have your Vds over L, that is E. Mu multiplied with E will give you Vx. So you have all these terms on the right-hand side. So now, interestingly, what you see is this W over L. This is called the aspect ratio of the transistor. It's the ratio of the width to the length. It's called the aspect ratio of the transistor. As a designer, this is what you have a control with. So if you are an analog circuit designer or a digital circuit designer, you will control the W over L value of the transistor to have different amount of currents for the transistor. As you see that the current is a function of W over L. So the designer's job is to fix what is the W over L. That's all the designer does. The designer does not care about anything else. Mu n is the mobility of the electron. You cannot change it. Cox is the oxide capacitance per unit area, material property. You cannot change it unless the thickness of the oxide changes, which the designer has no control over. VGS minus VT, of course, when you're designing it, you'll design it for a particular gate to source voltage, for a particular drain to source voltage, and so on. So this is what will determine your design. But a designer's job is to find out what is the W over L to get a particular amount of current, target amount of current for specific VGS and VDS values. So this is the equation that we'll be using a lot in our later classes. But remember that this equation is valid for a small VDS. This equation will be valid for a small VDS, and I'll tell you why. Now, before I go there, I want to also show the proof of MOSFET IV characteristics. So this is what the document that we are looking at right now. The PowerPoint presentation is Intro to MOSFETs. I have also uploaded the proof of MOSFET IV characteristics. So this is a PDF. And whatever we discussed till now, it's written over here. So maybe if you have not followed what we are discussing, just go through this particular document and it will tell you exactly what we just discussed. So you see that this is the bar which we represented as the channel. You are representing the unit amount of charge, and after a certain unit amount of time, the charge residing in this particular volume moves to the right side because the charge is moving from left to right. Right? So you can represent your current as the movement, the amount of charge multiplied with the velocity of that charge. That will actually give you the amount of current. Now, the same things that we discussed right now, that how do you represent the overall total amount of charge in the channel as a multiplication of W COX times VGS minus VT. And we wrote it down as VT. Here it's written as VTH. Both represent the same thing. It's the threshold voltage. And then you represent your ID current as a multiplication of velocity along with that charge. And then you represent your velocity as mu times dV dx. Now, this is the difference that with the PowerPoint slides. In the PowerPoint slides, instead of assuming your electric field as minus of dV dx, we just assume it's a dV as VDS and dx as L. So that was an approximation, right? You know that the derivative only works if it is a small change in the quantities. But VDS may not be a small change, may not be a small value, or L length may not be a small value. And in that case, the exact calculation would be done through this derivative, which is mu equal to minus dV dx. And then you do an integration instead of just putting VDS over L, what we did in the slides. So you can do an integration and you'll see that with the integration, we'll come up with the same formula eventually. You'll come up with the same formula if your VDS is very small. So now this was the difference. In the slides, what we assumed was, let me write this down. What we assumed in the slides is my dV dx is equal to VDS over L. That the voltage difference between drain and source is VDS, the length or the distance between the drain and source is L. Now, as you know that only if VDS is very small and length is very small, you can approximate dV dx as VDS over L. Right? So it is true only for small VDS. But if the VDS is not small, you cannot approximate that. You just keep it in the form of dV dx, do the integration, find out that the equation will look like this. Now, what is the biggest difference between the equation that I had shown in the slide versus this equation? In the slide, what I had, if I just go back to the slides, exactly. So in the slides, you had W over L times mu and COX times VGS minus VT times VDS. Okay. But in this case, as you see, that you have W over L, you have mu n times COX, you have VGS minus VT, you have VDS, but you have this extra term minus half VDS square. And that extra term comes in because now we have done an exact calculation instead of approximating dV dx as VDS over L. That's the only difference that I wanted to bring to your attention. But remember that you are assuming VDS is very small. If VDS is very small, VDS squared is even smaller. And if VDS squared is even smaller, you can neglect this half VDS squared part. And if you neglect the half VDS squared, the current becomes mu n times COX times W over L times VGS minus VT times VDS. That's exactly the same equation that we had written in the slides. So if your VDS is very small, this approximation holds true, and that's where you can reconcile what is written in the slides and what is written in the document over here. But if VDS is not very small, you have to consider that half VDS squared term. All right, so what does that tell us? So you have this equation, and this equation, as you see, that it has a first order term, it also has a second order term. Now, for different values of VGS, you can try plotting this particular equation. For different values of VGS, you can try to plot this particular equation. And then if you do a derivative, this particular curve that you're seeing over here, how to find out the maxima or minima of a curve. Again, you learned that in your high school math, that if you take a first derivative of this ID with respect to VDS, because you're plotting your ID with respect to VDS, if you take a first derivative of ID with respect to VDS, equate it to 0, then you will find out where your maxima or minima is present. If you take the second derivative and the value of the second derivative at the value of maxima or minima, if that is positive versus negative, that gives you whether it's a minima or a maxima, right? Again, something you learned in high school, that how to use derivative to find out maxima or minima of a curve. So here, if you do that, you will find out that this is a parabola. The graph will be a parabola, and the maxima of that graph will happen at this region, or this, or this, and for that ID max will be equal to half of mu n COX times W over L times VGS minus VT whole squared. So this is going to be your ID max, which is half of mu n COX times W over L times VGS minus VT whole squared. Of course, VGS minus VT is the overdrive voltage, W over L is the aspect ratio. Now, if your VDS is less than VGS minus VT, if your VDS, so as you see that the maxima happens at VGS minus VT, right? The maxima is VGS minus VT. If your VDS is less than VGS minus VT, you say, or you call the region of the MOSFET as triode region or the linear region. So basically the MOSFET is in the linear region when your VDS is less than VGS minus V threshold. When your VDS is more than VGS minus V threshold, you don't call it the triode region anymore. We'll call it the saturation region, and we'll see what happens in that case. Right? So this part, the left side of the graph, is going to be called the triode region. Now you might argue the graph that we have drawn and the equation that we have found out is basically a parabola. Why did we say that this will saturate and it will remain like this? Although it was kind of evident or intuitive from the energy band diagrams, because after a certain point, the slope of the energy band diagram does not increase anymore. So you do see a saturation. That's what is intuitive from the energy band diagram. But from the equation, we are not seeing the saturation region. Right? So what's the gap? What's the problem here? The problem is that, okay, so you can go through some of these numerical problems as well, just to make sure you understand the concepts well. But what I wanted to show next is what is happening in the saturation region. Now, what happens in this case after your VGS? So we saw that if VGS is less than, here. So if your VDS, if your drain to source voltage is less than V overdrive, if your drain to source voltage is lower than V overdrive, then we call your VDS is small, and then the previous equations that we had found out is valid. Because remember, the previous equations that we came up with was for a small VDS. Only because it was small VDS, we ignored the VDS squared term. If the VDS is large, you cannot ignore the VDS squared term. So for a small VDS, and what is the definition of small? Because small is a qualitative word, it's not a quantitative word. What is the definition of small? The definition of small is if VDS is less than V over drive, you say that you are in the triode region or in the small VDS region. If VDS is more than V over drive, you will be in the saturation region, and we'll show it why. Now, if you look at the channel for that N-channel MOSFET, once again, so you have the N-type source, you have the N-type drain, you have the channel in between. As you keep on applying a VDS and keep on increasing the value of VDS, what happens to this NP junction? So remember that there is P-type semiconductor in between, and there is N-type semiconductor in the drain region. So as you keep on applying a higher and higher drain voltage, right, a positive drain voltage, you are reverse biasing the NP junction, right? Because you're applying a positive voltage at the N side, and you're applying your P-type semiconductor, which is the body of the semiconductor. Let's say that body of the semiconductor is grounded. So you're applying a positive voltage on the N and have a ground on the P. So that's a reverse bias. What happens if you increase the reverse bias to a diode more and more? The depletion region becomes wider, right? Forward biasing a diode, depletion region becomes smaller. If you reverse bias a diode, the depletion region, that is the region where you do not have any majority carriers, keeps on increasing. This is the same thing that is happening here, that as you apply a positive voltage at the N-type drain region, your depletion region widens, which means the number of majority carriers near that PN junction, so that depletion region keeps on getting wider and wider. What is another way of saying it? That originally you had the source over here, the drain over here, and let's say you apply a positive voltage at the gate. So you created a channel between your source and drain by applying a positive voltage at the gate. What is meant by a channel? You attract electrons. The region just below the gate becomes more and more negatively charged with electrons. Your source was negatively charged with electrons. Drain was negatively charged with electrons. Now your channel is also negatively charged with electrons. So you have a continuous body of negatively charged electrons which can flow from left to right. That is the whole meaning of creating a channel, right? We understand up to this point. Now, the electrons are the majority carriers, correct? In this case, because source, you had majority carrier as electrons, drain, you have majority carriers as electrons. So electrons are the majority carriers in the N-type semiconductor, in the N-channel MOSFET. But if you apply a positive voltage at the drain, then you are reverse biasing this drain to body. So this is N and this is P. The body of the semiconductor was P. You're reverse biasing it. If you reverse bias the NP junction or the PN junction, the depletion regions become wider. That means there cannot be any majority carrier within the depletion region. How does the channel look like in that case? You'll see that the channel start behaving very strangely. The channel would start look something like a triangular structure. Why triangular? If you apply a certain amount of drain voltage, you will create a little bit of depletion region between the NP junction. Increase the drain voltage even more, you push the majority carriers away. Then the region over here does not have any majority carrier. You apply even more drain voltage, you just keep on widening your depletion region more and more. So after a certain point, your channel does not look like a rectangular channel, but rather somewhat like a triangular shaped channel. Question? So you're asking why is this N plus? Yeah. Right. So that's basically a choice. You can make them N plus if you want to have. So the more doping you have, the more amount of current you can create. So it's a choice of the. So there are multiple process technologies. You may heard about, let's say, Intel 16 nanometer, Intel 7 nanometer, TSMC's 3 nanometer, 1.6, like 16 angstrom, and so on. These different process technologies will have different properties. And they might say from the foundry that, oh, now we have doped the source region even more. So you can get more amount of current from the same device. So it's a choice of the device designer. The circuit designer has to work with whatever the device designer provides. That's a great point, that why does it have n plus in this diagram, and in the slides it has n. In terms of the physics, nothing changes, right? You still have electrons going from source or drain, or the basic fundamental physics, nothing changes. The value of the current, the number of electrons that you can source, the number of electrons that are present in the drain, all of those things change, right? If you heavily dope it. And again, n plus or n, that's still qualitative. What matters is the quantity of the n doping, right? That can still be different, right, in different process nodes. All right. So as you are applying a drain to source voltage, you keep on reducing the thickness of the channel on the right hand side. So the thickness of the channel is the full channel thickness on the left side. But on the right side, because the depletion region is widening and depletion region does not allow any majority carriers in it, the thickness of the depletion region on the right hand side will keep on reducing. And after a certain point, what would happen is that the thickness will reduce to a point. And that point is called, or at that, the VD at the particular VDS at which that happens is called the pinch off point. So your pinch off VDS is the VDS at which the channel on the right hand side toward the drain side reduces to just a point. And it's a pinch off point because it's basically just one single, the thickness is very close to zero. After that, what will happen? If you still keep on increasing your drain to source voltage, after that, what will happen is that the depletion region will become even more wider, and this pinch off point will start shifting towards the left. Right? So effectively, the channel length, after a certain VDS, the channel length keeps on moving towards the left. The channel itself the channel is not able to use the full length between the drain source and the drain. The channel gets pinched off, and that pinch off point starts moving toward left. And because of that, you do not have a continuous channel anymore between source and drain. However, you have a large amount of, you are increasing the positive voltage over here, right? Basically, that's what you're doing. So all the electrons that are present within this triangular shaped channel, the electrons are still heavily attracted towards the drain side because electrons are negatively charged, and you're making your drain more and more positively charged. So whatever electrons were present in this region of the channel, they will still move through, even though the channel does not exist. Because of inertia, they started with a certain velocity from left, and they are being attracted by this positive voltage on the drain side. Because of inertia, they will basically jump through this gap and land on the drain side anyway. However, because the number of electrons are now not changing anymore, so initially, if you apply a positive voltage, the number of electrons getting attracted from left to right, that just keeps on increasing, right? Because you can attract more and more electrons if you're increasing the voltage. But because the channel got pinched off and the pinch off point is moving toward left, after you are increasing the drain to source voltage beyond a certain limit, you cannot attract more electrons, but whatever electrons you had attracted, they just jump through this gap in between and land on the drain side. And that is the reason why the current saturates. The entire mathematical derivation is given here in the document, that how you can derive it. Eventually, you'll see, I'll not go through the derivation, but please look through the derivation. But what matters in this case is basically eventually you'll end up with the equation of ID, which is independent of VDS. In the previous equation, it was dependent on VDS. This was the previous equation for small VDS. This is for triode region or small VDS region. Triode region or small VDS region. And this is the saturation region equation. For triode region, if the VDS is small, this term is neglected, and then current is linearly proportional to VDS. Here, you have current, which is dependent on VGS, but not dependent on VDS at all. Right? There is no VDS term in the second equation. That means that the current becomes saturated with respect to VDS. So the first equation tells you about this region. The second equation tells you about this region on the right. Okay. Now, in a real MOSFET, you saw that it is not exactly flat. It's not parallel to the x-axis. There is a small slope. The reason behind that small slope is that here you had W over L. Here you have a W over L prime. And that L prime actually signifies the length of the channel after you have pinched it off. The original physical length of the channel was the length between the drain and source, the source and drain over here. But the actual length of the channel after the pinch off, that is basically the length of this triangular region, right? Which is much smaller than the original physical length of the channel. And that original actual length of the channel is the L prime that you see in that particular, the second term over here, this 2.16, this equation. And because L prime is not same as L, you have that non-ideality that it's not exactly flat. It will still depend on VDS a little bit because L prime depends on VDS. But to the first order, this term is independent of VDS. So please go through these equations at your own time. I'll not ask derivations in the exam, so you don't need to remember the derivation, but this will help you understand how the MOSFET behaves. So let's stop here. In the next lecture, we'll start looking into how to solve or how to look into these equations in even more detail and how to solve problems related to MOSFET.
Oh.
Yes.
I had a question about the gate capacitance of MOSFET. Is that like something? Is that like as a parameter? Is it considered like a non-ideality?